this sense of variance is like smoothness in a sense, right?
You may, it's depends. I mean, so we are in a finite space. I don't want to say smoothness. It is, yeah. In when you see in, yeah, at the moment, let me not use that word. It's
maybe it's overloaded. Yeah, thank you. Fine. Yeah, no problem.
But yeah. But when you go to continuum thing, yes, something that weighs quickly will be kind of considered to be less smooth because it has high derivative. Yeah. So if it has to be localized, then it has to quickly, but not a zero type thing, then it has to go up quickly and come down like Gaussian. Let's say you normalize so that the area under the curve is 1. Then it has to, if it has to be localized, it has to go up and come down, which means it has to have very high derivative at some places, and that then it is less smooth in some sense. The derivative is almost blowing up.
Yeah. Okay. I guess this word smooth is at least as loaded as variance, because I actually meant it in the sense of jagged functions, in the sense of Chinmay actually.
Okay.
But let me not confuse the discussion. Sorry. Thank you.
Yeah, but that point, let me say here we are talking localized, delocalized by looking at the domain space. Okay. You can, yeah. So values more or less don't matter here. Almost. So what we did last time was to prove these uncertainty principles. First one was that the L1 to L infinity norm ratio, if I take that as the measure of spread, then product of that for F and product of that for F hat is at least n, where n is the size of the group. And then we proved another one, if F has support SF and F hat has support SF hat, the product of the sizes, cardinalities of the support is at least n. Okay, so we proved these two inequalities. So let me just make a remark here. Yesterday I was talking to Kaushik and he pointed this out. See, in general, this we saw it can be achieved, right? I mean, so we saw that if n is PQ, then this is this. So by the way, this one also implies, yeah, so this one also implies that greater than equal to 2 square root n. Just by AMGM inequality, the sum is greater than equal to 2 times the square root of the product. So it is greater than equal to 2 square root n. And it is also again achieved if n is, let's say, p square. If n is pq, then one has support p and other has support q. Suppose p is equal to q, n is p square, then this will have support p, this will have support q, p also. So the sum of the support sizes will be 2p, which is 2 times square root of n. It is also achievable. But you see, it's not achievable. It's at this level, it is not achievable if n is, it doesn't see, you can't see how it is achievable if n is not a square, right? Because then the product will be. So in particular, if n cannot be factored like that, it can be much worse. I mean, this need not be achievable. So there are things on that line. And what Kaushik pointed out to me was there is also a theorem of tau. Extended it that if n is prime, then you certainly cannot factor it as a square. Far from it, you can only factor it as 1 into p, 1 into n. That's the worst case in some sense. You cannot factor into two equal factors. The two factors will have to be really opposite. I mean, one large, one small. So then you can get a much better improvement here. So if you take the delta function, then its support f hat is has full support. So in that case, you get n plus 1. So when n is a prime number, you can get such things. So I will not go in this direction, but it is an interesting kind of thing relating the number theoretic property of n to the this type of uncertainty, and it uses a little bit of algebra and so on. So and it's not relevant to me, and I don't know if it's particularly applicable. I mean, something being prime number and so on, whether that is particularly useful in application. So I will not go this side. But if someone wants to read up on it, most welcome. There's a I can give the reference later. Okay. And then I went on to other PQ uncertainty principles. So one thing that we did prove is that for 0 less than P less than 1 and infinity. Okay, P infinity, when P is between 0 and 1, I proved it. And I also, in fact, for PQ. So we proved an uncertainty principle for PQ when 0 less than P less than 1 and let's write it like this, 1 less than equal to Q less than equal to infinity. Okay, I may have not, okay, I did not actually quite get the proof. I made some stupid mistake, that's all. So I have written it into the notes. I will not spend time on it. So I will not do this. So the proof is fixed. I mean, it is a simple fix actually. It is done in the notes. So I will not do it. So we have an uncertainty principle for this. For this one. Okay. And what else do we have for? So there is also a uncertainty principle for P between 1 and 2 and Q between 2 and P dash, where P dash is the conjugate exponent. Okay, so maybe I quickly indicate that. I mean, so it's not particularly, we don't need it, but I'm just, it's just a chance to say something that is interesting. So let me indicate this. So how do you do this? So the thing is, it's something that is useful to know in analysis. The thing is, the Fourier transform, we know two things. So f hat infinity is less than equal to 1 by square root n times f1. And we know that f hat 2 norm is same as 2 norm of f2. So the Fourier transform, so there are two things. So we look at this LP. So sorry, P is 1 is here, 2 is here. So this is getting mapped to, sorry, this is getting infinity is here. So one is getting, L1 is getting mapped to L infinity and L2 is getting mapped to L2. And these are, so to speak, the operator norms, right? So operator norm is exactly the smallest number you can put here, so that, so if you look at the Fourier transform on L1 to L infinity has norm 1 by square root n, and Fourier transform from L2 to L2 has norm 1. Okay, so this is what we have. So it seems that, so what is the interesting analysis fact? If you don't know this, it is something that is useful to know. Whenever you have such a thing, everything in between here. So in this case, this one, for any P here, there will be a Q here, such that from P to Q, I can get an estimate like this. Okay, it will be an operator norm. From P to Q, I can get an estimate like this. Okay, so in other words, think of, we are interpolating from 1 to 2 by going P goes from 1 to 2. Then this Q goes from infinity to 2 in a certain way. How exactly does it go? So the way it goes is, you have to take, as I said, the LP spaces. Sometimes it is useful to realize that they have been indexed in the wrong way. Indexing by the reciprocal would be better sometimes. So how is the interpolation done? So let's say 1 by P, let's call it 1 by P theta is theta over 1 plus 1 minus theta over infinity in this case. I'm writing it in this specific case, but you understand what would be the general thing. If it was mapping L1 to something, so, and here q theta will be the corresponding
No,
interpolation.
Manju, is it infinity or 2?
Oh, sorry, sir. No. Oh, sorry. It is 1 and 2. Yeah, you're right. Sorry. There is no infinity here. It is between 1 and 2, right? The domain spaces are 1 and 2. Then the corresponding q theta will be having the same, take the same convex combination. But here 1 corresponds to infinity and theta corresponds to so you understand, right? So 1 goes to infinity, 2 goes to 2. Any p in between, you can write 1 over p theta as a convex combination of reciprocal of 1 and 2. So let this be where theta is in 0 to 1. And use the same theta to define q theta. So in other words, if you fix p, then that determines theta and that determines the q. Okay. So this is the Riesz-Thorin interpolation theorem. That says that I'm writing it all in the specific setting, but it is completely general. Whenever you have a linear operator like this, and you know what to generalize here. If I, instead of 1 and 2, I may start with A and B, and here it may be C and D. Perfectly okay. The same thing holds. Satisfies. Has norm less than equal to, you take the norm from 1 to infinity to the power theta and norm f from 2 to 2 to the power theta. So let me just use that notation here. Satisfies norm of the Fourier transform from p theta to q theta will have this type of interpolation. Okay, it will be, this will be the bound on the norm. Sorry, what is this infinity here? Sorry. That is theta and this is 1 minus theta. Let me just see if I got it reversed or. When theta is 1, we are taking p equal to 1 and q equal to infinity. Then you should get the L1 to infinity norm, namely 1 by root n. So in this case, this is just 1 by square root n to the power of theta. Okay. So this is the statement. So this is the Riesz-Thorin interpolation theorem. The general statement you understand. I have written it for the specific context, but I hope it is clear. It's a very beautiful theorem, amazing. And its proof is even more. It's a spectacular proof using some complex analysis, Fragment Lindelof and stuff like that. It is a spectacular proof. People who are interested can look at the proof. But otherwise, it's just useful to know this, that whenever you have that sort of thing, you can interpolate and get some P to Q inequalities. But it's not that you can choose both P and Q in between. You choose a P, there will be a corresponding Q for which you will get an inequality like this. Okay. All right. So then, so this, what this leads to is, in our case, what this tells you is that consequently, so in our case, what is theta? So in our case, what is theta? So let's work it out. So theta, so fix a P. In 1 to 2. Then what is theta? So I want 1 by P equal to theta plus 1 minus theta by 2. Implies theta is what? Theta by 2 is equal to 1 by P minus half, right? 1 by P minus a half times 2. Am I right? So that will be 2 over P minus 1. Did I make a mistake here? Is it okay? Which I can write if you want as 1 over p minus of 1 minus 1 over p. So it is 1 over p minus 1 over p dash. Okay. And what is q? You have to use this to get q. 1 by q is theta by infinity, which is 0, plus 1 minus theta by 2, which is theta is this. Theta is 2 over p minus 1. So 1 minus theta is 2 minus 2 over p divided by 2, which is 1 minus 1 over p, which is just 1 over p dash, the conjugate exponent, right? So what this is telling is, thus, the Richthofen interpolation is saying that the Fourier transform, if you look at the Fourier transform, then the Q norm, which is P dash, now we see that it is P dash, is less than equal to, what is the norm of P times some constant, which is, what is that constant? It is 1 over root n to the theta, which is 1 by n to the theta by 2. What is theta by 2? It is this one. Half of 1 over p minus 1 over p dash. Okay, so I have scrawled it like this, but I hope it is clear. It is just 1 by root n to the theta I have written like this. Is it clear? So what we originally had, so you see now the interpolation point is very clear, right? So we had infinity norm was bounded by 1 by root n times the L1 norm. 2 norm was equal to the 2 norm. So the P dash norm, so if you go between 1 and 2 here with P, it turns out that the conjugate, the other side, what Q you get is exactly the conjugate. This is because once here you have infinity and 2. But so the P dash norm will give us exactly that P dash norm of Fourier transform is bounded by P norm of Fourier transform times 1 over n to the half of this. So this is a famous inequality called Hausdorff-Young inequality. One of you was asking the other day, I think it was Agniva. I'm not sure if he's here, but Hausdorff-Young inequality. Okay, so this is the Hausdorff-Young inequality, and what this will also hold in the continuum setting later. We won't have any n there. Okay, so it will turn out slightly differently. There won't be a factor of n here, but something else. Okay, some constant will be there. But this, if you did not know Richthofen interpolation, this is a good point to take home from this lesson. So now we have this. So this gives you that. So one consequence of this. So what is an uncertainty principle? So let's now state a P dash uncertainty principle.
Sir, but it will look the same as what we got for PQ. 1 by P minus 1 by Q. In place of Q, we get P dash.
Well, except that I didn't get it, I messed up, right? Or
yeah, but you also told the step to fix, like replace that one inequality. So is that we can get.
Right. You are right. Actually, that is true. But yeah, actually you're right. So did I get? No, actually I'm not sure if I remember this correctly. Okay. So maybe, yeah. So just look at the notes for this. Okay. I don't remember.
Yeah, you told that we can use that in the P infinity proof. We used a bound on F1.
No, I said this, but the end result I may not have remembered properly.
No, I tried to do it, and we can actually get it.
You get this, is it? Okay.
Yeah. Yes.
Okay. I have written it into the notes, which I can look up, but maybe you are right. Maybe it is exactly the same we get. So what we now get is something like, yeah, what will be the PP dash uncertainty then? 1 second. Yeah, so we get that. So here we get that norm FP over. So when we want PP dash uncertainty, we are going to multiply like this, right? Now, by taking this norm Fp with norm F hat P dash, we will get that that is greater than equal to n to the 1/2 of 1 over P minus 1 over P dash. And similarly, with F hat in place of, reversing the roles of, so you can reverse F hat and F. You may think that I have to take F check and F. It's the same actually. Norm wise, they will be the same. So you can take F, you can put norm F P dash less than equal to this quantity times norm F hat P. So this ratio will also be the same. So I will just get n to the 1 over P minus 1 over P dash. So let me write it. So this is the uncertainty principle for P dash uncertainty. Now I will ask you to, I will leave it as exercise, or you can look up in the notes. I don't know if I have written it or given it as exercise. Extend it to PQ uncertainty for P is again between 1 and 2. And Q is, here I did the extreme case of P dash, but you can go all the way up to 2 in the form so it is Sahasranand, whatever you said, that is the quantity that will come. This I remember, but I didn't remember that it was exactly the same for the other case also. But you get an inequality like this. So P dash will just be replaced by Q. So to go from P dash to PQ is like earlier I had from P infinity, right? I did the uncertainty for P to infinity and then I went for P to Q where Q was less than infinity, between 1 and infinity. So similar point here. I already have from P to P dash. You do it also for Q between 2 and P dash. Okay. I will leave that as exercise. Is it okay? So these are, maybe as I said last time, when I pile on inequalities, it may seem a little too much and overwhelming. What you need to remember is only these two. Okay. So if you are finding this a bit overwhelming, too many inequalities, I can't remember what the hell is going on. You only need to remember this one and this one, 1 and 2. Okay. So that's all we are doing. Any questions, comments? See, uncertainty principles is an old subject, but what I have taken, the presentation I have taken from a very recent paper. Last year, famous computer scientist Avi Vigdasan and I think maybe his son, or I'm not sure, Yuval Vigdasan, they published a paper on uncertainty principles. Made a remark which is very insightful to me. They say that the idea is implicit in many papers of uncertainty, but it was not made explicit. So let me emphasize the idea again if it was not made explicit in the presentation. So primary thing is this one. Okay, so the whole thing, their approach is primary uncertainty principle is this, which comes directly from the fact that L infinity norm is bounded by 1 by root n L1 norm of F hat, and this one. From that we get this. Okay, and then if you want to prove any other uncertainty principle, their idea is the following. Suppose you want to use some other measure of spread, okay, some other measure of localization. This is one measure of localization. Okay, so if you want some other measure of localization, so suppose, so let me just write that remark here. So let h0 of a function be the L1 to L infinity norm ratio. Okay. So first the primary uncertainty principle which I got is that h naught of f into h naught of f hat greater than equal to n. Okay, so comes from two things. Actually, norm f infinity less than equal to 1 by root n. Norm f hat infinity less than equal to L1 norm of f. I will write slightly differently, and the fact that norm f hat 2 is equal to norm f2. So these are the two things, right, which I just now used in the interpolation. These are what is behind this. Now you may see I did not actually use that when I got this. It's just a way of phrasing it. What I used here was I used this inequality for f and f hat, also for f hat and f. So in other words, I used the duality. But equivalently, you can use Plancherel. Okay, so that's essentially the same thing. So reversing role of f and f hat or saying this, you can use either way. So I will just write as they write that this comes from these two facts. Now, suppose you have some other, you want uncertainty principle for some other measure h. Measure as in a general sense of measurement. So you have some other way of measuring. It could be some LP to LQ norm, or it could be some kind of entropy, etc. So there is an one for entropy. I won't say what is that entropy. The Shannon entropy. Let's not go into that, or support size. So now try proving that your new measure of uncertainty is greater than equal to this old measure of uncertainty to some power alpha for all f. This has nothing to do with Fourier transform. Okay. This is a general question of how your h is related to this h naught. Suppose you manage to prove that. Then the corollary is an uncertainty principle for h, namely h of f into h of f hat greater than equal to n to the power alpha. Because you just h of f is more than this, h of f hat is more than h naught of f hat to the alpha. Product will be more than n to the power alpha. So you get, this is the insightful thing, and essentially this is what we did. What we did, if you look at support size, for example, the second one, the Donohoe-Stark uncertainty, what we proved was that the support size, where is that? Sorry, one second. Where is that? Where is it actually?
So it is right side of inequality 2, right? That's what you mean?
Sorry, here it is. Yeah, right. Here we put that the support size, if that is my measure of the size, support size is bigger than, you cancel the square root ends here, L1 norm by L infinity norm. So for the support size, if h of f is support size, cardinality of support of f, then we proved that h of f is greater than equal to h naught of f. That's what we did, and hence we get this inequality. So that was what we have done. That's what we have done actually. So this is I found this very insightful. Yeah, because I had seen uncertainty before. One of the leading experts on uncertainty principles is our own chairman, Thangavelu. He has a whole book on uncertainty principles in harmonic analysis. Nothing is there written in discrete setting there, but it's all in level of Euclidean space and Lie groups and Heisenberg group and so on. But he's a leading expert on uncertainty principles. And when I was a master student, he gave me a whole course on this. So I had seen, but still I found this simple insight quite insightful and explains many things. It doesn't give you all the uncertainty principles that are known, but it is nevertheless insightful. Okay. Any questions, comments? So, as I said, things to remember: 1, this one; 2, the Donohue-Stark. Now I will go on to a little more on uncertainty principles. Okay, so uncertainty principles. So I have written here continued. Let me write robust. Okay, so here let me tell something about the style of modern analysis, which is also something that makes it closer to what is actually applied. Okay, see what when you take an applied from point of view of applications, what will a theorem like this say? Let us, okay, what does it say about any application? I have not explained. We will come to that. But imagine that such a theorem is there. Will it ever say anything about application? Strictly speaking, no, because in real world, no function is ever zero anywhere. Okay, so zero is not an attainable number. I mean, no number is attainable in some sense. So when we talk of some, if you are talking about an image, okay, the image is an image can be written as a function on a square, right? I mean, you give the grayscale value, you give a number, okay? So that way, image can be captured as a function on a square. Or if you have a sound signal for a duration, you can capture it as a function on an interval. However, such functions, I mean, when we say real numbers is a model for that. So when we say at a particular time, the pitch of the sound or the grayscale value is a number, it is really a model. It doesn't make, I mean, it's a real number, but okay, strictly speaking, whether it's 100 digit makes any sense, we don't know. But we model it as a real number. So whether it is actually exactly zero at any point is a meaningless question. It is never. So a theorem like this will be vacuous because every function will have full support, and so this product will be anyway n square. So there is nothing that it says. So what to make? So this is a general principle also in mathematics. What you need is a robust version. What is robust version? So let me now say it in mathematical terms. Whenever you have an inequality, so think of an inequalities like, for example, Cauchy-Schwarz. So just to explain the point, what is robust, or it's also called stable versions. So let's think of an inequality like Cauchy-Schwarz inequality. It says that the inner product UV is less than equal to norm of U times norm of V, with equality if and only if V and U are collinear, means V and U are linearly dependent. So either V is a multiple of U or U is a multiple of V. Okay. So this is the standard way of saying it. Again, when you actually apply it in the real world, it may never achieve exact equality, and nothing will be exactly linearly dependent, possibly. But what matters is, so you ask a robust question. So robust version would be suppose equality is nearly achieved. In Cauchy-Schwarz. Is it true that U and V are nearly linearly dependent? That would be the robust version. So you have to quantify the nearly in both cases. What do you mean by nearly achieved? Well, you can think of maybe it is not quite less than this, not quite equal to this, but maybe the inner product absolute value is 0.999 more than 0.99 of this. That would be nearly, okay, or more than 1 minus epsilon of this. You have to similarly quantify what it means for U and V to be nearly linearly dependent, okay. So is it true? In this case, it is true. I mean, I am just taking this very simple example to say what it means to look at stable version. So it is the style of modern analysis that you always look for stable versions of theorems, and they are also what really can be applied to the real world. If you have an inequality which like this, if it was not stable, its applicability to real world would be highly doubtful. Okay, so but it is stable, so it is actually useful. So what is uncertainty principle in the robust or stable version? Okay, so let me say, so let's come back to our own setting. So G is a finite abelian group. So let me just write all the setting again. And N is the cardinality of G. So let's say that F is a function on this G. So we want to say that if F and G are nearly supported, cannot be, so question is, what is the kind of question that we are wanting to ask? Okay, so here, look at the Donohue-Stark. It says that you can't have two small sets, one in G, one in G hat, such that F is supported on this set and F hat is supported on that set. Both cannot be too small. That's what this is saying. Now the question is, can I have two sets, both of which are small, such that F is nearly supported on this and F hat is nearly supported on the other? Meaning maybe it is, so is it possible? So we can't have both F and F hat delta functions, right? But can I have F such that it puts most of its L2 norm at one point and F hat also puts most of its L2 norm at one point? Let's say 99% of their L2 norms at one point. Is that possible? So that is what robust versions will tell us. Okay, so for that I have to make quantitative what nearly supported means. So for F from G to C, this has nothing to do with groups, okay? But okay, let's say F from G to C. So we say, so fix some P and epsilon. So P is in 0 infinity. You can take 1 infinity if you prefer. Okay, so if you can take 1 infinity, but epsilon is in, okay, epsilon belongs to looks weird. So let me write delta here. Delta is just a number in 0 to 1. Okay, so a set contained in G is said to be an approximate P delta support for F if I take F restricted to the set, okay, and look at its P norm. Then I capture most of the P norm of F. What is most of? 1 minus delta. It is F times indicator A, P norm is at least 1 minus delta times F P norm of F. So in that case, A is said to be a P delta approximate support. Is the definition clear? It's not unique. By the way, support is a unique. Support is all those X where Fx is not 0. Whereas here, first of all, if I can always take A to be the whole set, that is a P delta support. I haven't said A should be the smallest set such that this happens. And there may be no the smallest set. You may remove one point here and add another point. It may still be a P delta support. We don't care. I don't need that sort of a definition. So we will just say there can be a lot of P delta supports. I don't care. So let's say A is a P delta support if F restricted to A has most of the LP norm of F. Is the definition clear? So this is a definition. Now we can state this is the definition of approximate support. So now I will state a theorem and then prove it. Okay, so I will state two theorems. The second one is the more important one. The first one is easier, so we will do that first. Maybe I will have to postpone part of the proof of the second one to the next one. So theorem is this. See, so for this G being a group and all is not necessary, is clear, right? So I can also talk about f hat support. Okay, so now let's take G finite abelian group. So suppose f from G to complex numbers, and of course then f hat is a function on G hat. Suppose A is a 1 epsilon approximate support for F, and suppose B, A is a subset of G and B is a subset of G hat. Suppose B epsilon is a 1 delta approximate support for F hat. Okay, inside G I take something that captures most of the L1 norm. Up to 1 minus epsilon factor, it captures 1 minus epsilon proportion of the L1 norm of F is captured by A, and 1 minus delta proportion of the L1 norm of F hat is captured by B. Then we say that the cardinality of A times the cardinality of B is at least, is nearly n. Okay, so we will have to lose a little bit here, 1 minus epsilon into 1 minus delta. Okay, so if you set epsilon equal to 0 and delta equal to 0, you get back Donohue-Stark inequality. When epsilon is 0, it means A is a support of F. I mean, A supports F, right? A contains the support of F and B contains the support of F hat. If I put delta equal to 0, in that case, the product will be at least 10. But this is the stable version of that, one stable version of that. Here, I say one stable version because I only use, I mean, I don't mean it is a stable version because I use the one norm here. A more powerful theorem will be doing the two norm, which I will come to next. Any questions about this whole? The philosophy should be clear. The philosophy of stable theorems is a very important one. That is the style of modern analysis, actually. So I hope this is something that I have conveyed. Okay, are there any questions? The proof is very easy for this one. I will do it now. Are there any questions? No? Okay. So how do we prove this? Once you think of it, it is not difficult. I mean, so let's give a proof. Let's look at how did we get the, first of all, how did we get the other uncertainty? The Donohue-Stark basically started with L infinity norm of F hat bounded by 1 by root n times L1 norm of F, right? Infinity norm of F hat is bounded by one norm of F, and then now we can't say we will not use the full support. What we did earlier, just to write and erase, earlier I just wrote this is less than equal to F infinity times the support size of F by root n. This is not going to be useful for me because I don't want to use the full support size. I mean, A may be much smaller than the full support. Full support may be the whole group. I don't want to use that. So I have to use the definition of approximate support. How do I do that? Well, by definition, this is bounded by one over 1 minus delta times F times indicator A L1 norm, right? What is the definition of approximate support? That A captures 1 minus delta portion of this. So in other words, L1 norm of A is at most 1 over 1 minus delta times L1 norm of F restricted to A. And that's what I have written. It is bounded by 1 over 1 minus delta times L1 norm of F restricted to A. Now, this is obviously less than or equal to L infinity norm of f times the cardinality of A. Right? What is F indicator A? You write the sum. Okay, so this is actually
So, sir, 1 by 1 minus epsilon, right? We use epsilon for A.
oh, I see. So which is epsilon. You are right. So maybe I change it up in the here. Okay, you are right. So let's say this is delta and this is epsilon. So statement is okay. So here it is for F, it is 1 minus delta. Okay, so I do this. And this one is just sum over f of x in A, right? So I can bound it by the L infinity norm of f times A. I don't have to write L infinity norm of A restricted to A because that's the same. Because outside it is 0. The L infinity norm of f is achieved on A. So it is L infinity norm of f times cardinality of A. And exactly the same way, if I start with L infinity norm of f bounded by 1 by O10 L1 norm of f hat, okay, which is bounded by 1 by O10. Now it is 1 minus epsilon because B is a 1 minus epsilon approximate support for f hat, and that is bounded by 1 by square root n into 1 minus epsilon times L infinity norm of f hat times the cardinality of B. Okay, so now multiply both sides. I mean, forget everything in between. Multiply this side and this side. What do you get? L infinity norm of f hat multiply. So we get f hat infinity into f infinity less than equal to 1 over n times 1 minus epsilon into 1 minus delta times infinity norm f into infinity norm f hat times cardinality A, cardinality B. So you cancel this and then you get cardinality A into cardinality B is at least n times 1 minus delta 1 minus epsilon. It's okay? Very simple. Very easy actually. More or less the same. I mean the proof earlier we did not use, we just put the bounded by infinity norm, but if you put the 1 epsilon norm then you can just do that. Is it okay?
Sir,
Huh. Yeah.
the remark that you made about that f infinity being achieved on A, that need not be true, right? Like we can still upper bound whatever is the maximum on A by f infinity. That's why this holds.
That is true, but outside A it is okay. Yeah, you right. No, you are right actually. That is true. So since I'm talking about approximate supports, I mean it would be very weird, but it is certainly possible. What Sahasranand is saying is that I made a remark that the infinity norm of f is achieved on A. That's not correct. If it was actually 0 outside A, that would be true. For example, if you imagine a very large space and the function is kind of small everywhere, at one point it is large, let's say. Still, for L1 norm, this can be an approximate support. Although it is large at one point, this may well be an approximate support is possible. So in that case, infinity norm is achieved outside of it. You are right. Thank you. But it can be bounded by the infinity norm of f. That's very correct. I will, yeah. Is that okay with everyone? When we are talking about one norm, approximate one norm, if the space is very large, at one point it may be large but still be outside of the approximate support. Any other questions, comments? Okay. So that was the one delta. This is for robust version for p equal to 1. But what I want to say is the bigger theorem, this is what Donoghue and Stark proved. And so I want to state that. So this is the, again, what they proved is same setting. So as before, okay, let me just write. So F from G to C, F hat from G hat to C, and let's say A contained in G, 1 delta, 2 delta. That's the whole point now. Okay, so 2 delta approximate support. For F, and B contained in G hat, 2 epsilon approximate support for F hat. Then we still have cardinality A into cardinality B greater than equal to something like that. It's just that 1 minus epsilon minus delta squared or something like that. It is not so important. I mean, it is to some extent important, the dependence on epsilon delta, but point is when epsilon and delta go to 0, you get back the, this also includes the other Donohue-Stark inequality for exact supports. You put delta equal to 0, epsilon equal to 0, it recovers that inequality. Is okay? Is it all right? Okay. So now I want to say how do we prove this kind of thing? This is actually more non-trivial than this one. We will do it. It's actually quite nice. I mean, the proof is nice, and I want to do this. Yeah. So how much time? Oh, already 12:59. So maybe I will postpone the entire proof to next time rather than try to start it now. I will postpone it to next time. So yeah, so is there some other remark I wanted to make? Okay, I can leave you an exercise. So let me just see in my notes. I have it. I have written it in my notes, but yeah. So here is an exercise I will leave you with, which is actually easy, not too difficult. So it's a good exercise, but don't. I mean, this theorem is a bit more involved than. But what I can give you is an exercise. Suppose A is a 1 delta.
It's 1 o'clock.
Approximate support for F, and so it's a mixed thing. So B is a 2 epsilon support for F hat. Then show that cardinality A into cardinality B is greater than equal to something like this, n into 1 minus delta square, 1 minus epsilon square. Okay, you try a proof like here. Maybe you have to do a bit more. Remember Plancherel and all that. So this is an exercise. So this is a mixed one. So here notice 1 delta and 2 epsilon. Okay, here it is 2 and 2. I will stop here. We'll continue next time. Any questions, etc. I am here to answer.